Welcome back. We continue our lecture devoted to the review of the compact Lie groups. So as we mentioned in the previous lecture, we have a special kind of the measure on a compact Lie group, which is called the Haar measure. To be more precise, let me formulate this as a result, so it will be easier for us to refer later. So this will be like this. So put it like this: theorem. And we would name it the Haar measure. Haar measure. So let G be a compact Lie group then there exists a unique measure let's write it down, mu, which is defined on the border sets and with the values in 0, 1 interval, border sets in G, such that the associated with mu integral has the following properties. So the first is the usual, first two is the usual linearity property. So put it like this: A, it will be that integral of g of any function f1 plus f2 d mu is equal, maybe move a little down, let me make it larger, integral of g of f1 plus f2 d mu is the same as integral of g f1 d mu plus integral over g f2 d mu, and b is also, that's a typical property, so this is cf d mu. C is a constant, so you can take the constant out. So this will be g and this will be f d mu. So those are the usual properties. The next property is that actually the measure is normalized. That means the measure of the group G is 1, so that we can write it down as d mu is equal to 1. And then we have two properties related to the invariance of this measure. So that means C, and put it like this, and that means for every h belonging to G, I have here the integral over G, and this will be f, and this is h, G, d mu G is equal to G, and this will be f, G, h, d mu G. This must be equal just integral over G, and that one is f, G, d mu G. That means that shifted functions from the left or from the right, it still get the same integral, have the same integral. And then we have finally E is that integral over G, and that one is f, and I put here G minus 1 d mu G is equal to integral over G, and that one is f of g d mu g. So here we should add where the functions f, f1, f2 from g to r are measurable and integrable. Maybe we should say like this, measurable. Let's write simply integrable. So we guarantee that all these integrals are finite and C belongs to R. So now let me point out the properties that are expressed here. So here, of course, this property means nothing else than that the mu of the whole group G is equal to 1. That means the measure is normalized. And that one is related to the fact that mu of A, so put it like this, G, H, A for any set, measurable set, is the same as mu of A, H, and that one is equal to the mu of A. So this gives you the property D. So here, yes, we have, that means simply that the measure is invariant with the left and the right translations. And the final means simply is related to the fact that A minus 1 is the same as mu of A. The last property follows actually from the uniqueness of the measure, of such a Haar measure. Notice that if you have here Haar measure, so put it like this, margin, which is a unique and satisfies the properties, these properties that I mentioned above, that it is invariant and invariant with respect to translations, it's normalized, so there is only one such a measure. So if I define a new measure and I put it like this, n of A is the same as this particular Haar measure, and I put here minus 1, so one can easily notice that in such a case, this m tilde already satisfies the same properties as it is as the other one. That means the properties that it is invariant and is normalized, so that implies clearly that this must be equal to m of A. So m of A. So since we have the uniqueness, so of course we have only such a measure. And now let me erase this, this is not needed. Let me erase it and let me introduce the next topic. Actually, we'll be interested in the generalization of this integral into the case of the Banach spaces. In such a case, such an integral will be called the Bochner. And since here we are dealing with a particular measure, Haar measure, so we'll call it Bochner-Haar integral. So let us begin. So this will be related to the vector valued functions. Vector valued means in this case the functions will be taking values in a given Banach space. So let E be a Banach space and assume that G is a compact Lie group, with equipped with the Haar measure. Haar. And let me using mu on the Borel set of G, and goes to R. Okay, R. It's okay. Oh, maybe. 0, 1, like this. So, consider a function, a vector valued function. And the function is f that goes from G to E. And this function will be called measurable. We say that f is measurable, or mu measurable, if and only if it is a pointwise limit of mu measurable simple functions. So let me explain it maybe in more details. So start maybe what is a simple function. So I put it like this little margin, and let me explain. So a simple function, a function which is S from G to this Banach space E is simple if it has only finitely many values. If S of G is finite. And that means S of G can be written using the values, for example, x1, x2, xn. In such a case, one can also consider the sets. So put EI, by the definition, this is equal S minus 1 of xi. So I is equal 1 to n, and those sets are basically subset of G. So the S, so the simple function, is measurable clearly if and only if the sets EI are measurable. So we know what means a simple measurable functions. So in such a case, now we can use the sets, measurable sets EI. We can simply write that my function S of x is equal, and I put it like that. This one is equal, this is equal, I equals 1 to n. And now I take the characteristic function of this EI, put here, no, it's not correct, I should write here G, and now I put here like this G, and then I put here xi. So this is a vector, this is a scalar. This is a vector, this is a scalar. Should notice that this is actually a convex linear combination of the vector. So it's a convex linear So it's a linear combination of xi. Convex would be for integral. So this is G sub. So this is the we are getting here. So what is the characteristic function? I think everybody knows, which means maybe I should write it down. E of G is equal 1 if G belongs to E, 0 if G does not belongs to E. So that's the characteristic function. Okay, so in such a case, what does it mean? So it means, in more precisely, f that goes from G to E is measurable if and only if there exists a sequence Sn of, maybe like this, there exists a sequence of simple measurable functions Sn, and it goes from G to E, such that for every G belonging to G, limit Sn goes to infinity, Sn of G is equal f of G. That's it. So once we have it, we can say the following definition. Maybe I don't need a definition. Maybe it's better to write. In such a case, we say that f is also integrable if limit Sn goes to infinity integral over G. And now this integral is actually scalar, so that means we have here norms of these functions, and in this one is equal to 0. So this so clearly, so we can put it like that. So integral, and we can put it like this. Since let's put it like this. Since we can define maybe like this. Defined Sn of G defined for a simple function, measurable function S of G equals, let's write it down, I is equal 1 to n, and this is how we had before, of G, and this is xi, the integral, and this is exactly our Bochner-Haar integral. So integral of G, and this is S d mu, which will be exactly equal to sum. This is I is equal to 1 to n, and then this is measure of the EI, and this is xi. So notice that this integral is a convex combination of elements xi of these vectors. So then and we put that the limit, maybe like this, by the definition, we put that this, in such a case, the integral of f d mu is exactly equal to limit as n goes to infinity of our approximating sequence, and this will be Sn of d of mu. Yes. There are obvious properties of this integral, so please remember, so maybe important property is the following, so you maybe put it properties, so maybe first that if you have integral f of d mu of g, if you take the norm, you will be getting that this is the other Haar integral, and this will be norm of f of g d mu of g. So we have this inequality, and also the Bochner-Haar integral satisfies the properties, the same properties AE as the Haar integral. So, so we will be using them later, just for certain, in the case when we'll need certain constructions, which we'll call the averaging techniques on over the group G. So let me maybe go to the next page and let's make a proposition. This will be kind of a maybe just to play a little with this integral. So put it like this: proposition let G be a compact Lie group and E, maybe no and, E a Banach space and F from E, sorry, from G to E, a continuous function. Then F is integrable. Maybe write it down like this: Bochner-Haar integrable. I think let's do it like a proof. And notice first, so since G is a compact manifold, it is metrizable. And Therefore, so we can assume, say, by the metric dxy, and by compactness of g, f is uniformly continuous. It is uniformly continuous, so which means particularly that for every epsilon larger than 0, there exists a delta larger than 0, such that for every g and h belonging to g, if you have here dgh smaller than delta, then that one implies, this one implies that this is f of g minus f of h is smaller than epsilon, and we will use this inequalities, this condition, as we'll show it, as we'll denote it by star. So this is our condition star. So next we will construct the sequence of the Sn. Next we construct the sequence Sn of measurable simple functions. So how it goes? So take for epsilon equals 1 over n, we find n, and we find delta, this is our delta n larger than 0, such that star is satisfied. Very good. Then, with the help of induction, we construct families, put it like this, families, finite families, finite families of Borel sets Let's call this Borel sets E, I, N, I is equal 1 to M, and finitely many, satisfying the properties. So what are these properties? Let's start with the first example, number 1. So these are disjoint sets of the EIN intersection EJN is empty set if I is different than J. And the second one, actually, it's a cover. So this is I is equal to 1 to MN, and this is EI is equal to G. And then we also have 3. Yes, that's for every x belonging to EI. So this is also n here. EIN, this is n partition. We have here the distance between x, satisfying the properties, and I need to choose. So this is not x, first of all. for every 2G, for every G and H belonging to E, I, N, and we have here the distance between G, H is smaller than okay, delta N, smaller than delta N. Good. Okay, so this is number 1, 2, 3, and we have number 4, which means that for every 1 smaller than J smaller than N plus 1, so this one is N plus 1 partition, means this is the next family. This is where we use the induction, so this is I smaller than N, and we have here that the following in partition is a refinement on the previous partition. So this is J N plus 1 is contained in E I N. This is a refinement. So that's a not complicated construction, because what we will do is the following. We have this delta N, so now maybe I show how the sets are constructed. So suppose we have here this is my G, I represent it as a square, and now we have the partition. So what do? I take the balls of the radius delta N divided by 2x, and of course I can choose the finite. Okay, suppose I cover it with these balls. I cover it with these balls, like here, here, and here. So we have this part. We have this part. Let's say we have the cover with the balls. We choose the finite subcover. So for example, I take as the first set, I take that one. So this will be like a first set. So that will give me the set, for example, E1. Then I go to next one, and that means the next one is going to be, for example, what is remaining from the second ball. So, sorry, let me do it like that. What is remaining from the second ball, for example, this will be this. And this will be E2. And then I go to the next one, so for example to the third ball, and let's say what is remaining from the third ball after removing from it the previous sets, it will be this portion. So this will be E3. And then you have here the other one, so let's say that one, we take another one, so this one is maybe this one, for example, or you have another one, and this will be like E4. And you continue like this. If you continue, so for example, that one will be the next one, and finally the last one. And we got all the sets. So if you have the next partition, so you just simply use the finite balls that you go to the next partition, you take 1 over, so you take the next n, you get the smaller balls. The smaller balls will partition you the sets E1, E2, En into the refined partition. And that's how this partition is done. So that's clear that this is satisfied. Of course, You notice that each of those balls, for example, has a center. So in such a case, we can choose from these balls a set, from this sets one particular point. So let me maybe say like this: we choose x, I, n belonging to E, I, n. So that's an element that belongs to this set, and he is going to be fixed for us. So now, once I have these points, now I can, maybe I should write not x, I should write g, because this is all in the set. So put it like g, I, n, and g, I, n belongs to the E, I, n. Choose for all I belonging to 1, 2, mn, and define. So here we have here Sn of G will be equal, and here we have sigma I is equal to 1 to mn, and then you have here characteristic function of this set I, n, again G, and here I put here G, I, n, which was this, sorry, not this one, but f of G, I, n. So G belongs to G is a simple function. That's our simple function. So now, of course, notice. So let's say like this. So now let's show that the condition. So we will show for every epsilon larger than 0, there exists an n such that for every n larger equal than n, I'm having here that limit, that norm of Sn, that for a fixed G belonging to G, that means this is pointwise. For every epsilon there exists an n such that, and this will be S n G minus f of G smaller than epsilon. Indeed, choose epsilon larger than 0 and let 1 over n, where n is natural number, be smaller than epsilon. Then we have here, for this particular term, for n larger equal than n, we have here like this. This one is equal to Sn G minus f of G. It is equal. So this will be equal. So this is what? So we have that G belongs to certain x J n, put it like J, we call it n I. So in such a case we have that for some I, so that will be equal to S and G will be equal, in this case, just simply f of G I and minus f of G. This is the norm, and here and in such a case because both of them belongs to this, and since GIN, since GIN and G belongs to the same set IN, so that norm is smaller than epsilon. Smaller equal to epsilon. Actually, smaller equal 1 over n, smaller than epsilon. And that proves it. So now, once you have it, so actually notice that notice that this is true for all functions. So you can see clearly here that for continuous function, this actually is true for every g. So that means there exists that actually we have here uniform approximation. Actually, this is a uniform approximation, because you see this is true for every g. Basically, we didn't use the choice of the first. We chose the epsilon and we say this is actually true for every g. So actually we have here that one, that this is Sn of g minus Fn of g is smaller than epsilon for every g, and that clearly implies that the integral of this Sn g minus f g, maybe I should put here like this, this is 1 over n, 1 over n, so this would be 1 over n. Okay, I should. So for every g, you can use this should be 1 over n, so we can get smaller than 1 over n, and the limit as n goes to infinity integral over g of Sn minus f d mu is smaller than 1 over n g d mu, which is 1 over, limit smaller equal limit n goes to infinity 1 over n g d mu, which is equal limit n goes to infinity 1 over n is equal to 0. So yes, it is integrable. So we got it done, we finished it, so we got it done, so that's it also. Of course, let's compute something, let's integrate, so since we know already that this is kind of an integral that we have just described in certain way how to compute it, so maybe we should compute it, so put it like this, example, let's compute an integral, Bochner-Haar integral. So let's consider the group G, which is exactly the compactly group S1 that we introduced before. So what is S1? I will just describe this group as EI tau, where tau belongs to R. So those are elements which are contained in this unit circle. So this is considered with the multiplicative structure, of course. So now I also consider an Banach space. So my E is the Banach space, let's write it down, of continuous functions from S1 to R. So these are the continuous function phi going from S1 to R. Phi is continuous, and the norm of phi, which we also put some kind of infinity here, is equal supremum for tau belonging to R, and this will be absolute value of phi EI tau. So that's the norm. This is our norm. So what is the function? what is the function? So we have the function, I put it like that, defined. F that goes from our G, that means the circle, to E, is defined as follows, that F defined on E I tau is equal to, okay, this will be equal to sine, and this will be tau plus t. So that means this is a function. This is supposed to belong to the function. This belongs to the E. So it's a function of so E of tau is equal to, it's a function in this space. So maybe let's write it down. That's actually, maybe sometimes it's better to write it that phi of t is periodic, 2 pi periodic, because we can use this identification. But in certain way, so if you just remember that if you have a function on the circle, you can think about these functions as a periodic functions on the interval 0 to pi. So in a certain way, this means periodic. So I will define this function 2 ways so you can see immediately what it is. So first of all, I will define this function. So that's my function f e I tau, and now 2 ways. So I put here e I t will be equal e I first I write it down like this, sine tau plus t. So it's well defined. Sine tau. Oh, okay, but actually you can even write it down here. This one is equal imaginary part of e I tau times e I t. This is an imaginary part. So how am I going to compute this? So how I'm going to compute this integral? So take partition. So we will construct the sets En. So let's say we will use the partition of the circle. We use the partition of the circle. We use the partition of the circle S1 by the roots of identity. So this will be the roots of identity, with solution here. So we can write it down that these roots actually, by the roots I put here like this, n to the power j. So what are these roots? So this means this roots of identity gives me a partition. So this is gamma n is equal to e I 2 pi divided by n. So let me make a picture. So here we have the circle. This is our circle. And now we have here this roots of partition. So this is 1, 2, 3, 4. So that's my gamma n. That's it. 1. So the next one is will be gamma n squared, gamma n cube, etc. So it gives you a partition set. So we can define the sets for that partition. E j n. So it will be arc on the circle, which will be starting at the point, for example, starts at the point gamma j, and it goes to the gamma j plus 1, like that, but that one is not, does not belong here. Does not belong here. So what is this? So let me indicate it. So here we have the first one. So this one is like a closed, open, and this is this arc. So that gives me E1. Then I go to the next one, and I have here this one belongs, this one does not, and this is this one. So this is E2. And then I go to the next one. So this belongs, and that does not belong to this partition, and this is my E3. And so on. You can get it. And of course, we can choose in this case, we can choose for each, and that points, the points that are specifically chosen here, put it like this, red. So this will be the point gamma n j belongs to the E jn, is this fixed point that we choose from each of these sets. So in such a case, since we have here the integral over g of f over g of f d mu is equal limit, and this one is equal limit, and that one is n goes to infinity, and I can say that it will be equal to over g, and this is Sn d mu. So what is our Sn? Our Sn of g is equal to I is equal 1 to n, and here we have here characteristic function. So this is characteristic function on ei, n of g, and then here we have here e, like this, the imaginary part of e, maybe let's write it down just simply f of gamma n I, like that. Just write it down like that. It's easier to. So this is n. So let's use the formula. So this means it is equal limit n goes to infinity. So here we have the integral. So I just take the sum. I is equal 1 to n, and this measure of this each of the sets ei is just simply, this is exactly one end of the circle. Whole circle has measure 1. It's a Haar measure, so it will be just simply 1 over n. And then here I have here this value, so that means this is the value which we have it. This is imaginary part. This one is imaginary part, and what do I get here? And this one is equal to, and here is the function. I put it like this: e. This is r. We have it here. So let me look again. So you see, this is that the function. So I just copy imaginary part of ei tau. Ei tau times, and this is the function. So I just put here I. No. This has to be taken at that point, so this will be like this. Just simply imaginary part of gamma n I times ei, and this is dot instead of tau, so that's a function. So that means ei dot, if I put here tau, this will be like, yeah, that's our function, ei tau. So maybe because this is an element, I could actually write it down. Okay, that's it. Maybe I write it down like this. Put here tau, then we can understand it better. So it is equal to limit n goes to infinity 1 over n, and this is the sum of gamma and I is equal 1 to n, and then times this ei tau. We understand that this is the variable of the function, and what do I get here? That one is equal to 0, because this is the sum of all roots of the identity of order n, so it must be equal to, this is equal to 0, so okay, it is equal to 0. So we got it, so that means this integral is equal to 0. So let me write it down. So it goes gamma n 1 plus gamma n 2 plus gamma n minus 1, that's the last root. So this will be the same as 1 minus gamma n 1, and this will be 1 minus gamma n to the power n, which is equal 1 minus 1, 1 minus gamma n I is equal to 0. Okay, so that's the value is equal to 0. So that function is a 0 function. So we computed this integral. And then this completes this particular section. So we just wanted to have kind of a possibility of using this notion. So let's go to the new page and let's talk about the further properties of the compactly groups, or the additional properties of Lie groups. So maybe let's assume maybe I put here okay, first assume that G is a Lie group, not necessarily compact, Lie group. Okay, definition. A subgroup, I put here H, and we usually write subgroup of what? Of G, so we use the inequalities to denote that this is a subgroup of group G, is a Lie subgroup. That's the definition, so put it red. Is a Lie subgroup of G, if H is a submanifold of G. And the second is B, for two Lie groups and I put it like this, G1, G2, a group homomorphism and let me write it down, phi from G1 to G2 is called a Lie homomorphism, Lie homomorphism if phi is smooth. This is it's a homomorphism of the manifolds. And now What are those additional properties? So let me formulate this as a theorem. A. If G is a Lie group and H in G is a closed subgroup, then H is a Lie subgroup. So closed subgroups of the Lie groups, exactly those. B. If phi between G1 and G2 is a continuous homomorphism between Lie groups then phi is a Lie homomorphism. And that's very strange. Continuity here implies differentiability. And C. If H, and we denote it using this symbol right here. Let's write it down. Subgroup, and if this is a normal subgroup, I make it a little triangle here. So this is G, means is a, let's write it down, normal Lie subgroup if Asian is a normal Lie subgroup of the Lie group G, then the quotient space, the quotient group is a Lie group. Let's go further. If H is just a subgroup of G, is a Lie group, is a Lie subgroup, sorry, it's a Lie subgroup of the Lie group G, then the normalizer of H in G, and that means this is this set, let's write it down. So normalizer of H, by the definition, the set of all G belonging to G is such that this is G H is equal HG as a set, subset, is a Lie subgroup. Therefore, the Weil group, maybe it's not so. So the Weil group, the so-called Weil group, of H in G, which is exactly, this is this set, so let me write it down. So this is while group of H equals, this is N H divided by H, is also a Lie group, is a Lie group. So we got it. So these are the properties that we will be assuming that we know. We don't prove it then. I would say I advise anyone who is interested in studying further, deeper, the properties of the Lie group and the algebras. There's a whole universe there to discover. Just to go and just get the proper resources and study them. For this course, we need only certain type of the properties that we'll be using in our constructions. So for a moment, we will not need more than that. So let me now go to the maybe next topic, and I just introduce it at the end of this lecture, and we will be continuing in the lecture 9. So let's see what it is. So maybe assume. So usually we would say like this. So if you let me write it down. Definition. Let X be a Hausdorff space. So this is a topological space. Be a Hausdorff space. And again, we consider G a compact Lie group. And suppose we have here an action of the group G on the space E. So suppose phi, so action means I have such a map. So the action must be continuous, suppose is a continuous map. And here, of course, it's supposed to be action such that we have here the following. So let me write it down. So for every, maybe I should add it later, so just simply write it down. F phi, and I put here, so G goes first, so this is G phi of H of X is the same as phi G H of X. So this is for every G and H belonging to G and every X belonging to X. So here, as you notice, it is kind of difficult even to read it. So that's why instead of writing, maybe I do it here, instead of writing phi gx, we will just simply writing g acts on x, like that, g acts, like a proper g acts. And in such a case, this property here can be simplified, simply means that g acts on h on x is the same as gh acting on x. It's much simpler, it's easier to read. So the action means that you have here this property of the superposition. So then you have here the second property. So if you take the neutral element in this, so that means neutral element in the group E, so that means you will be getting X, where E is neutral element in G, and this is for every X in X. So that means again this property is that EX is equal to X. So that map, that continuous map phi is called the G action on X, and this is topological action in our case because we have continuity. So put it here, topological. So this topological action of the group G, topological action of the G on X. X is a topological space. So to be more precise, such an action actually, since X, you see, if you look here, you can see that that in such a case, so this means this is G actually times X to X, satisfying this property. So this is continuous, write it down, continuous, and then you have here GHX is equal to GHX. So we have here X one second, X no, something. Oh yeah, X. Just a moment. This continues. Okay, maybe it is a good moment to stop because I see that I can see clearly that my tablet that I'm using is now refusing to do anything, absolutely anything. So it's got really overcharged. So I believe that means that simply we are not able to continue. So I will start next time with the group actions, and we will maybe I repeat what I couldn't finish now, and this topic will be repeated. Let's say so. I'm apologizing because I'm not able to continue with the present setting because of technical complications. So thank you, and I will continue next time.